In this lesson, we're going to go over calculating accelerated position. And from various contexts, we've already talked about position without acceleration. So just to kind of recap that, we basically had a formula D equals RT, which we've translated to some different symbols. X is what we're universally using for distance, and rate we're calling velocity, so V, and then T. So these are the same, but neither of these account for, well, what if the object we're talking about, say a car, bike, a person running, doesn't matter, is speeding up or slowing down, in which case their velocity does not remain constant. So this formula is an extension of these, and you can see it has this extra piece right here. So let's go ahead and go through each of these pieces. Again, little f means final, little I means initial, and we're using x to mean position. So we have essentially right here our final position is going to equal our initial position, and then we add that to our initial velocity. And since it is accelerated motion, that means that that velocity will be changing. So our initial velocity um, will not be the same as our final velocity. And just keep in mind, we do have a formula that we could find that final velocity. And that's this one right here. Final velocity equals initial velocity plus acceleration times time. Okay, T is time in seconds usually. A is our acceleration. And that could be positive or negative. So if it's negative, um, a negative acceleration means we're going down or to the left, one of those two. Down or backwards, I guess I should say. And we have time squared. So time again. Basically, to use this formula, we plug in all the information that we have and put it in our calculator and see what we get for our final position. Now, if an initial position is not given, we assume 0. And if an initial velocity is not given, we also assume 0, unless we have a really good reason not to. So that being said, let's take a look at our first example. And what I'd like you to do on each example is give it a shot on your own, compare with someone else after having paused the video, of course, and then unpause the video and check and see how you did. So here's the first question, and you should write it down because each example is something that you'll see again later in the form of homework or something like that. So we have Jimmy is running at 2 meters per second. He sees his rival in the distance, so he speeds up with an acceleration of 0.25 meters per second. Per second squared, I should say. How far will he run after 9 seconds? So go ahead, see what you can figure out based upon what we've been doing. It's just one more formula in your mix. See if you can figure out what his distance would be or his position. Go ahead and pause the video, give it a shot. All right, well, hopefully you went through the question and you circled each important piece of information and you attempted to label what type of information it is. So Jimmy is running at 2 meters per second. So this is him at the start, and this is a velocity, and it's an initial velocity. And then we see we are told specifically that this 0.5, that this is an acceleration, so this is A. And then we're asked how far will he run after 9 seconds, so this is a time. Now, since this is an accelerated motion, we have to use this position formula that we just went over. And then what we're going to do is we're going to substitute in each value that we have into parentheses. So an initial position is not given, so that is 0. Our initial velocity is 2. Our time is 9 plus 0.5 times 9 seconds. 9 seconds squared. I forgot our acceleration, so this it should be right there. But it doesn't matter where we put it. So 0.5 again. That's what got me confused. So this normally would be right here. But it really makes no difference because we're multiplying it anyway. Alright, so we go ahead, we multiply. 2 times 9 is 18. Now, order of operations is going to tell us that we have to do exponents first. So this piece first, and 9 squared is 81. And then 0.5 times 0.5, that is 0.25. And then we do 0.25 times 81. And that gives us 20.25. We have our 18. We'll add our 18 to that. And we get for our final answer 38.25 meters. So, given that he starts at this speed, accelerates at this speed, for 9 seconds, he will cover about 38 meters. Now, it's important to note, and is not necessarily something that we'll do at this level, but it's important to note that most people, in fact, all people, all vehicles, cars, trucks, whatever, they can't accelerate indefinitely. They eventually get to a top speed where they can no longer accelerate anymore. And that's something like in 11th grade physics, something that you would have to account for. Okay, so now we have Jimmy is riding his bike at 5 meters per second. He can accelerate at 1 meter per second squared. And he can brake, so that means decelerate. And we have a negative 2 meters per second squared because braking is a deceleration, so the acceleration is negative because he's essentially slowing down. So if you have a negative acceleration, generally slowing down or speeding up in the negative direction, so whatever that happens to be, and accelerated, we're going positive or speeding up in our positive direction. And just to be clear, generally our axes are like this, so these are our positive directions. Up and to the right are generally our positive directions. Alright, anyways, give these two questions a shot. It asks, what's his speed and distance after 4 seconds of accelerating? So I'll put up here a reminder. Our final velocity formula is this. And our final position formula is this. So go ahead and give each of these a try by pausing the video and seeing what you can get. Alright. Hopefully you got these right, but let's see. We're looking for speed and distance. So these are positions and a velocity over here. So this 5 meters per second, that is an initial velocity. He can accelerate at 1. So this is an acceleration. And brake, decelerate. We have a negative 2 right here. So this is also an acceleration. So we do have two different accelerations depending upon what we're asked. So in the first section, we're asked, what is the speed and distance after 4 seconds? And our key is accelerating, so we'll be using this one right here. So speed, that'll be velocity. And we plug in our numbers. And we follow the order of operations, and we'll get a final velocity of 9 meters per second. And then for distance, we have final position equals initial position plus initial velocity times time plus a half at squared. We aren't given an initial position, so we'll say that's 0. His initial velocity is still 5. Our time is 4. Then we have 0.5 times 1 times time squared. The time I'm given is 4, so time squared is 16. So following the order of operations, I multiply before add, so I'm going to multiply 5 and 4, get 20. And I can multiply all these, I'll get 8. And we see his final position is 28 meters. So after 4 seconds of accelerating, if he starts at 5 meters per second, we can see that he is then going 9 meters per second, and he's traveled 28 meters. Now, if we look at the next part, it asks for his speed and distance after 2 seconds of decelerating. So we're going to assume that we're going off of our initial conditions, so we're still at 5 meters per second, but instead of using this 1, we'll use this -2. So his final velocity is initial plus AT. His initial velocity is 5. His acceleration then is -2. And we're decelerating for 2 seconds. So that gives us 5 minus 4, because -2 times 2 is 4. -4. You could type this all in your calculator. It will give the final answer to you, which is 1 meter per second. You slow down quite a bit. And then we have our final position formula. And we plug in the information that we have. Again, we aren't given an initial position, so we'll assume 0. He starts out at 5. We're decelerating for 2 seconds. His acceleration here is -2 because we're decelerating, and our time is 2 squared because this is our time. Up here, this was our time. I forgot to mention that. And then 2 squared is 4. And we'll plug all of this in. 5 times 2, order of operations. And then this will give us -4 if I multiply all that. And that gives me a final position of 6. So if he starts slowing down, he will end up going 1 meters per second, and he will travel 6 meters while he's slowing down. All right. Only a couple more. There's lots of parts to this one. So Kevin drives down the road at 15 meters per second and is speeding. A cop sees him, unfortunately, and pulls out as Kevin passes by. So this is going to be some tricky thinking right here. But as Kevin passes by, so this will be our initial condition, is as he passes the cop. From rest, the cop accelerates at 2 meters per second. So we want to find, after 3 seconds, what's the distance between them. After 5 seconds, 10 seconds, and 20 seconds. So a lot of position formulas right here. So let's see if you can figure out the distance between them for each one. I probably won't go over necessarily all of them, but go ahead, pause the video, see if you can figure out what's the distance between them in each of these cases. Okay, hopefully you figured it out. Let's do this one 3 seconds. So we have Kevin and the cop. So Kevin is going to be using the same formula as the cop. Makes no difference. And I won't rewrite the formula for the cop, I'll just substitute in different. Alright, so our initial position is 0 is when he passes the cop. He is going 15 meters per second. His time is 3, because this is a time. And this is where I got the initial velocity for Kevin. And this would be the acceleration of the cop. So this is only the cop. So Kevin is not accelerating. So his accelerating is 0. I'm not given acceleration for him, so no acceleration. So this whole piece here doesn't end up mattering for him. So we see after 3 seconds after passing the cop, Kevin has traveled 45 meters. Because 15 times 3. Now the cop, same formula, except the cop's initial position is 0. The cop's initial velocity is 0 because the cop's just sitting there. So that's what this whole from rest, that means the cop's initial velocity is 0. But the difference is the cop is accelerating. And he's accelerating at 2 meters per second squared. We're going to give him 3 seconds to do that. Alright, so after 3 seconds, the cop, if we multiply all this, now this 3 squared, that's 9. And half of 2 is 1, times 9 is 9. So, the question asks, what is the distance between them? Well, I would subtract these two to get the distance between them. So, 45 minus 9 is 36. So we have 36 meters between them. Let's try after, I'll skip the 5 seconds. Let's do the 10 seconds. Let's see what happens after 10 seconds. So we'll have Kevin and the cop once again. And then same formulas. Initial position for Kevin is 0. He's going 15 meters per second. We're going to give him 10 seconds this time. And he is not accelerating, as we discussed just a moment ago. So after 10 seconds, Kevin has traveled 150 meters. We're wondering, well, where's this cop? Now, I half-boxed that. That's not the answer. Let's see what the cop's doing. So the cop, initial position 0. His initial velocity is 0. So this middle thing ends up not mattering for him. But he is accelerating at 2 meters per second squared. And we're going to give him 10 seconds to do that. So 10 squared is 100. And then he will have traveled 100 meters. So what's the distance between them? Well, 150 minus 100, 50 meters. So let's do the last one, 20, and we should hopefully see they're getting awfully close, right? So Kevin, and I'm not going to go through the whole explanation here. He's essentially 20 times 20. Wait, 15 times 20. My bad. 15 times 20. So he is going to have traveled 300 meters. And then the cop is initial position 0, velocity 0, acceleration 2. And then we're going to give him 20 seconds. 20 squared is 400. So now we see Kevin is very lucky because the cop has passed him. So the cop must not have been interested in him for whatever reason. Now, I think that's the last one I wanted you guys to do. And if so, then you'll be starting your worksheet. But if not, let's see. Nope. Let's see how many more. Yep. Okay, so this is the last one. Oh, this is great. Very important problem. So Kindle throws a ball straight up at 5 meters per second. How high is the ball after 3 seconds? Now, I will give you a hint in a minute. So if you get stuck, unpause the video to get the hint of how to do this. Alright, if you unpause, that means you wanted the hint. So here's the hint. It's not spelled out, but if we're throwing a ball, there's an implied acceleration. That acceleration is the acceleration due to gravity. So whenever you have a gravity question, you're not going to be explicitly told to account for gravity. So it's your job to know, hey, if I'm throwing something up and down or if I'm dropping something, that means gravity is in the mix. So it is in the mix, and your frame of reference is going to be important. So if we draw a quick picture, the ball would go up, right? And then it would come back down. And there is a little key here that I'll ask in a minute about this ball at this peak. But for now, the ball is going up at 5 meters per second, but it experiences gravity downward at negative 9.81 meters per second. All right, so now with that little hint, our hint is acceleration is implied to be negative 9.81 meters per second squared, even though it isn't spelled out in the problem. So go ahead with that new information, see if you can figure out how high the ball is after 3, 4, and 5 seconds. Let's go ahead, pause, give it another try. All right, let's see what you came up with. For 3 seconds, again, we'd be using this formula. Pretty much the same thing over and over again. So our initial position is implied to be 0, wherever Kindle happens to be. Our initial velocity is this 5. So we should go through and label the information we have. So this is our initial velocity. And here is our time. And here is our A. So we put in all of these things. Now the sign on the 9.81 is very important because it goes opposite of the direction of our velocity. So we want to make sure we get it right. And time squared is 9. And we could type all of that into our calculator. I'm going to go ahead and do the accelerated part first. And I get minus 44.145. And then I have 15. And apparently Kindle needs to throw better, because if we subtract this, we do get a negative number. That wasn't intentional, but it is what it is. So what does this negative position mean? Well, it tells us this problem makes absolutely no sense. It means Kindle is standing on the ground. She throws her ball up, and it goes up, but not for long, before it craters down through the ground with a huge explosion, and she probably is dead now. So this is not what we want to happen. It obviously would stop at the ground. So common sense would tell us it actually just lands at point 0. So all of these other ones, the 4 and the 5 seconds, won't make any sense. They'll be an even worse case than this one. But let's go ahead and try it. Let's try the 4 seconds. And just to see what we would get, the initial position is 0. The initial velocity is 5. And then our time now is 4. Plus 0.5 AT, negative 9.81. And then time squared, that'll be 16. So if I type in the accelerated part first, I will get minus 78.48. Right here I have 20. And then when I combine those, we get an even worse crater of negative 40 or 58.48 meters. So that means she threw this ball up, and for somehow, some way, it smashes through the ground and falls 58 meters below ground. Doesn't make sense. Who made up this problem? She should probably throw at 50 meters per second. That might make more sense. All right. Now, I had said I wanted to do another question based on this, so let's try that other question. And that is, first of all, let's make this make more sense. Let's say she throws it at, I don't know, 40 meters per second. This is very unrealistic. She's basically gun at this point. But sure, 40 meters per second. How high is the ball after 3 seconds? I'm going to change that question to something completely different, something a little bit more challenging. And that is, how long until the ball reaches its highest point. And then the follow-up question to that would be, how high does the ball go? And our drawing for this would be, of course, Kendall is throwing the ball, and it goes up, and then it reaches this peak, and then it comes back down here. So the question is, how long does it take to get to this high point? And, well, how high is this high point? So, pause, give it a try. Okay, if you're unpausing, then perhaps you got stuck. So here's a hint. And then give it another shot. The hint is, at its highest, just picture that ball as it gets up to the top, we actually know the final velocity. The final velocity at the top is 0 because as it goes up, it will slow down until it reaches 0. And then when it reaches 0, then it'll start falling. All right, pause and give it another shot. Okay, this is our initial velocity. This is our final velocity. So we'll use this formula. And we don't know the time. We're actually being asked, well, how long? So that's time. This is 0. This is 40. And then gravity is negative 9.81. And time we don't know. So now we need to solve this equation. We'll subtract the 40 to the other side. Just like we would with math class. And then we divide by negative 9.81. And we get our answer that after 4.08 seconds, this ball has reached its highest point. So now we use this to know how far it goes. So if you didn't figure out that velocity, now's a good time to pause the video, give it another try. How high does the ball go now that we have a time? And here we go. This is our formula, and we'll put in our time. Our initial position, she is at 0. So 0. She gives the ball a nice push, 40. Time, we just calculated that, 4.08.5. We have our negative 9.81 and our time. This should be squared. So time squared, 4.08 squared. So follow the order of operations. You should do exponents first. So we do this piece first. And I get 4.08 times 4.08, and that gives me 16.6464. I'll multiply that times 0.5 and times 9.81, of course a negative 9.81. And that gives me this piece is minus 81.65. Then I have 40 times 4.08, and that gives me 163.2. And then I'll subtract that 81. And apparently, she threw that ball 81.55 meters. All right, at this time, you should be well equipped enough to try your worksheet.